Hello everyone, welcome to Mindspan Education. Last video we were looking at the central limit theorem. Central limit theorem states that if you have independent identically distributed random variable and if you try to look at the sum of these distribution, then the sum will tend to take the normal distribution as you increase the value of n. That means as you increase the number of terms in this sum. We have tried to attempt this. So we have these x1, x2, xn. These are IID. IID means independent identically distributed, and they so since all these are identically distributed, we can just talk about one of the distribution, and this distribution, that x1 distribution, has a finite mean and a variance that are well defined, right? And it will be again valid for all these random variables since all these are identically distributed and they are also independent. We tried to look at the distribution of the sum of these random variables, and there we are having few issues as we try to increase the value of n. Then the distribution were not converging as expected. Then instead of looking at the convergence of this distribution, what we have done, we have standardized this distribution and we have given this name. The standard form of this distribution is Zn, and how we have made the standardized version of this Sn by subtracting the mean of this random variable and dividing by the standard deviation. Now we try to look at the convergence of this random variable, that is the random variable Zn, and this Zn is nothing but the standardized version of this sum of this random variables, the standardized version of this Sn, right? And as we increase the value of n, then this standardized version of or this random variable Zn tends to take the shape of the normal distribution. So what exactly this central limits theorem states, that as you increase the n, or for the large value of n, the cumulative distribution function of this random variable Zn, that is the CDF of this random variable Zn, converges to the cumulative distribution or the CDF of this standard normal random variable, right? Or in other words, if you, for the large value of 1, the probability that this random variable Zn takes the value less than equals to little z is same as probability that this random variable, that is the standard normal random variable z, is less than this little z. If you look at here, we have like, this is a great result. How, let me give you an example. Let's suppose if you would have some 100 such random variable, so you would have some 100,000 such random variable, right? And let's suppose you do not have the information about the central limit theorem, and how do you find the distribution of the sum of these random variable? If I ask you, give me the distribution of the sum of these random variable, and let's suppose there are such thousands or 10,000 such random variable, what you will do, you will start convolving, and at the end you will have the distribution of the sum of those random variable. But the central limit theorem is remarkable, right? You do not have to do such expensive computation, right, convolving those distribution. The central limits theorem says that you can directly find. So how do you find? So instead of doing the convolution, if you are trying to find this probability, you just need to look up the normal table, right? Because what is this? this is the probability that this random variable z, and this random variable z is nothing but the standard normal. So how do we find this kind of these probability of standard normal? By looking at the normal table, right? You can just look at the normal table and you will have the answer to this probability. And once you have the answer to this probability, and central limit theorem says that for large n this will be same as this probability, right? So ultimately, in order to answer such kind of question, you will not have to convolve and get the distribution and then find the probability. You can just approximate using the central limit theorem, and these approximation are very much accurate, right? So this way the central limit theorem is very useful, right? So it gives you the accurate result, kind of accurate result, and it is also computationally less expensive, right? So I have written a few of the points regarding the central limit theorem that I wanted to talk about, and this will be just as a information so that you have much information about the central limit theorem. And last video I have also told you that I will be not looking at the derivation of this central limit theorem. Why? Because it requires the other fields knowledge to go through the derivation. Like if you want to go through, then you will have to go through the Fourier transform, and then you will have the this result. But let's not worry about that. Let's discuss few of the more points about this central limit theorem, then we will start solving the problem. So right, why this CLT, central limit theorem, is useful, that just now I have described, right? So it is accurate and it is less computationally expensive than doing the convolution. Now the central limit theorem, the statement says about the cumulative distribution function. What is this? This is the definition of the cumulative distribution function. So it says that for a large value of n, the cumulative distribution function of this random variable will converge to the cumulative distribution function of the standard normal random variable. It does not say anything about the probability density function, or in case of the discrete, it does not say about the probability mass function. Question is, will the PDF or PMF will also converge as we increase the n, or for the large value of n, will the PDF or PMF will also converge? Yes, it will converge, but for that you need to have some extra assumption, right? But yes, it will converge, right? So in order to talk about the convergence of the PDF or PMF, you need to have some extra assumption, and again I will be not going into those extra assumption, but the end point is that yes, PDF and PMF will also converge with some extra assumption. That is what I wanted to say. Now the other thing is that, so with this central limit theorem, we have the two assumptions that we are making. The first assumption is that all these random variables are identically distributed. Now the question is that let me also state the second assumption that we have made is that they are independent. So we are making the two assumptions in case of the central limit theorem, or the central limit theorem have these two assumptions. So in order to hold this central limit theorem, does these two assumptions are strictly that that need to have? Let's talk about that. So the first question is, do the random variable have to be identically distributed in order to apply the central limit theorem? No. If even they are kind of similar, right, then the central limit theorem that we can apply, right? It does not have to be literally the exactly identical. If they are kind of similar, then this central limit theorem will or can be applied, right? And there are other also generalized version of this central limit theorem. Again, we are not going to look at those generalized version of this central limit theorem, but it doesn't have to be literally identically distributed, right? So I think I answered this question. Now the second assumption that we have made in the central limit theorem about the independence, right? We have made the assumption that all these random variable will be independent. Does it have to be completely independent to apply the central limit theorem? We can apply the central limit theorem even if we have the weak dependence, right? So even if we have the weak dependence, we can apply the central limit theorem, it will work, right? So it doesn't have to be literally independent. So I think this questions also gets answered. Now the coming to the next question, that so central limit theorem says for large value of n, this CDF converges to the normal CDF, right? How large, or let me say the question in this way, that so central limit theorem says for the large n, can we apply the central limit theorem if we have n that is moderate? Usually yes, we can apply, right? So again, it depends upon that what kind of distribution we have, that if we have the distribution that is somehow somewhat symmetrical and unimodal, I mean to say it will have at least at most one peak, right? So if the distribution is kind of having the symmetry and unimodal, then for the less value of n, the distribution of sum will converge to the normal fast, right? So for I'm saying the same point, right? For less value of n, or the overall the distribution will converge fast, right? So but if we have some distribution that is that having the weird shape, right? It doesn't have any kind of symmetry and have lot of peaks and downs, right? In that case, we need to have some large values of n, or we need to have some large number of distribution in order to converge to the normal distribution, right? But usually if you have like around n is equals to 30, 31, 32, and the distribution have the symmetrical shape, and the distribution have symmetry, and it has kind of one peak, then it will converge to the normal distribution fastly, right? And usually it has been seen that for n is equals to 30 and 32, the distribution will tend to take the shape of the normal distribution, right? But again, it depends upon what kind of shape you have in the distribution, right? So the question was, can we apply the central limit theorem for moderate n? Yes, we can apply, right, depending upon the shape of the distribution, right? So these were the few points that I wanted to go through. Now let's look at the problems based on this central limit theorem. Let's try to look at the very first problem. We have a container, and the container receives packages. Each package has a random weight, which is an independent random variable that is drawn from an exponential distribution with the parameter half. We load the container with 100 packages. Calculate the probability that the total weight of the container exceeds 210. Let's first try to get the information out of this question. So we have a container, and what we are trying to do is that we are loading that container with the packages, and the weight of the packages is random. So the weight of the packages is random quantity, and let's first of all denote the weight of the packages with the random variable x1 and the weight of the second package is with the x2, weight of the third package with x3, and we are loading such 100 packages, and all these are random variable and they are taking the value from the exponential distribution, right? So all will have the distribution that will be the exponential distribution with the parameter half, right? And all these are independent random variables. What we have been asked that, so what we are trying to do, we are trying to load these random weights, and all these random weights are taken from the exponential distribution. We are trying to load these packages into this container, right? And we have been asked what will be the probability that the weight of the container, and how do we find the weight of this container? The weight of this container will be nothing but the sum of the weight of these individual packages, which is a random quantity that has been taken from the exponential distribution, exceeds the value 210. This is what we need to find the probability. And if we denote the sum of these IIDs, that is the independent identical distribution, with Sn, so this Sn is nothing but the sum of these random variable. So we have been asked to find the probability that this random variable Xn is greater than 210, right? So let me give you one more info that in general, like the central limit theorem, the problem of the central limit theorem will revolve around finding the probability of the sum of these IIDs, that how many such IIDs we will be adding, right? And so that it is greater than some quantity A, and this calculation turns out to be the probability of this calculation turns out to be some number, let's say P, right? So depending upon the problem, what if it is based on the central limit theorem, you will have these three quantity that may be asked. So in the problem statement, what will be given, maybe you will be given these two quantity and you will be asked what will be this probability, or maybe you will be given these two quantity and maybe you will ask that how many such random variable you need to add in order to achieve this probability, right? Or maybe you will be given these two quantity and you will be asked this, right? So the central limit theorem ultimately will revolve around finding these quantities, right? If you look at this first problem that we have described just now, we have given that the sum of these 100 such IIDs exceeds 210. What's the probability of that? So we are trying to find this quantity, right? So how do we proceed? We know that this sum will not converge as expected to the normal distribution. What we need to do, we need to make the standardized version of this sum. And how do we do that? We just need to subtract the mean from this distribution. So we are trying to find this probability that this random variable Sn is greater than 210. So in order to make the standardized version of this distribution, what we do, first we subtract the mean. And what is the mean of this random variable Sn, right? So what is Sn? So this Sn is the total weight of the container, and this total weight of the container is the weight of the individual package, right? And each of weight is having the exponential distribution with the parameter 1 divided by 2, right? So how do we find the expected value of this random variable Sn? Since all these random variables are exponentially distributed and they are independent, each have the parameter lambda, that is 1 divided by 2, what will be the expectation of a single random variable of this exponential random variable? The expectation of this exponential random variable would be 1 divided by lambda, that is 2, right? And we have such 100 random variables and each of are independent, then the expectation of this random variable Sn will be 100 times 2, that is 200, right? So subtract this mean first from this random variable and do both sides, right? Because ultimately we have to find this probability, so that is why we need to carry out this thing on both hand sides so that we have the equivalence of the equation. Now next step is to divide by the standard deviation of this random variable Sn. And how do we find the standard deviation of this random variable Sn? So this this random variable, that is Sn, right, and each one is again independent and each have the exponential distribution. So what is the variance of one random variable? That is the variance of this x1. It is nothing but, we know if it is exponentially distributed, then the variance is 1 divided by lambda square, right? So that would be 4, right? The variance of this one random variable is 4, right? And all these are independent, so the variance of this random variable Sn, will be, we have such 100 and each one have the variance 4, so that will be 400, right? And what will be the standard deviation? The standard deviation is nothing but the root of the variance, so root square of the variance, so 400 ka root square will be 20, right? So we need to divide this by 20 and we do on the both side, right? So we have got our standardized version of this random variable, and this equation will be same, or this probability calculation or this probability will be same, right? So let's denote this standardized version as Zn. So now this Zn is a standardized version of this random variable Sn, and it is nothing but divided by 20, right? And we have seen what central limit theorem says, that for large value of n, right, here n is 100, for large value of n, this random variable, that is this random variable Zn, can be approximated as a standard normal random variable, right? So this is nothing but the probability, let me write probability, that we can write this as a Zn is greater than half, right? And by central limit theorem we can say this will be approximately equal to finding the probability that the normal distribution, standard normal distribution, so this Z is a standard normal distribution, is greater than half. So by how we are saying this? Using the central limit theorem, right? Now we just need to look up the table, the standard normal table, right? That so that this in order to find this probability, right? Let me first of all put this normal table in front of you, then we will have the calculation of this probability. So now we have here the standard normal table, and this standard normal table gives you the probability of this standard normal random variable, such that let's suppose if this Z is random variable, normal random variable, so this table gives you the information about this probability that Z is lesser than equals to this value, that is this little z, right? So here we have this calculation that the this normal random variable is greater than half, so we can write this as 1 minus the probability that this random variable takes the value less than equals to 0.5, right? And what is this? This is nothing but the, in terms of the CDF notation, it is nothing but 1 minus the CDF value. So this is how we denote the CDF calculated at 0.5, right? So we can just look at what is this probability, and we can get it from the standard normal table, that Z is probability that this random variable, that is the normal standard random variable, is less than 0.5. So how do we find? You just need to look at 0.5. 0.5 is here and 0, so it is 0.6915. So this probability is 1 minus 0.6915, and if you calculate, that will be approximately 0.3085. Alright, now let's look at another version of this same problem. Now let's look at this problem. A logistic company loads a container with 100 packages. The weight of each package is modeled as an independent random variable following an exponential distribution with parameter lambda is equal to half. The company wants to choose the maximum allowable container capacity C such that the probability that the total weight exceeds the capacity is at most 5%. What is the value of C? Let's first of all try to understand the problem, and let's try to get the information out of this problem. We have again 100 package, and these 100 packages we are loading onto the container, and container will have some capacity. The weight of each package is random variable, and all these weight of the packages are taking the value, are a random variable, and all these are taking the value from the exponential distribution. So let's suppose this is the weight of this package x1, the weight of the package is x2. All will take the value from the exponential distribution, and all these random variables are independent. Now, so this exponential distribution have the parameter 1 divided by 2. This information also is given in the problem. Now the company wants to choose the maximum allowable container capacity C. So maybe this container, so what we are trying to do, we are trying to load these packages into the container. So this container will have some maximum capacity C. So the company wants to choose the maximum allowable container capacity C such that the probability that the total weight exceeds this capacity is at most 5%. So what's the requirement? The requirement is that probability that the total weight of the container, so the total weight of the container will be sum of these packages. So the total weight of container should so the company wants to choose the maximum allowable container capacity C. So the total weight of the container that company wants to choose, that is C, such that the total weights exceed its capacity. So the total weight exceed its capacity at most 5%. The probability of the total weight exceeds this capacity is 5%. So this probability is 5%. That means 0.05. Alright, so again, as I mentioned that here we have this known, right, and this is also known, and we have to find this unknown, right, and this problem will again fit into the central limit theorem, right. So we are looking at the probability of this random variable Sn, and this random variable Sn is nothing but the sum of the IIDs, right. So what we can do, how we can proceed, as we have proceeded for the last problem, right. So again, first step is to make the standardized version of this random variable, and how we do that. And this probability will be same as the probability that this random variable Sn. So we are going to make the standardized version of this one. So how we are going to do that? First we will subtract the mean, and the mean that we have seen from the last problem is 200, and we are going to do this both side, so c minus 200, and we have to also divide with the variance, and variance we have seen is 20, and it is equal to 0.05. Right? So this is the standardized version of this random variable Sn, and let's say that this Zn is equals to Sn minus 200 divided by 20, and this will be equivalent, or this will be equal to, or we can treat this random variable as a standard normal random variable, right? So what we are trying to say is the probability that this random variable Zn is greater than c minus 200 divided by 20 is equals to 0.05. So now what we are saying from the central limit theorem, that this can be seen as, or we can treat this Zn as a standard normal random variable, right? And this probability can be written as 1 minus probability that this standard normal random variable takes the value less than equals to c minus 200 divided by 20, and this is equal to 0.05, right? So probability that this random variable is less than this quantity is equal to 1 minus 0.05, that will be equal to 0.95, right? So here again, now we are treating this random variable from the using the central limit theorem as a normal random variable. So this probability is equals to 0.95 for what argument, or we can say we can write this probability as the CDF. So CDF calculated at the value c minus 200 divided by 20. So what value of this argument, the probability will be 0.95. So we can simply look at the normal distribution table, and we can find that for what value of this, that this probability will be equal to 0.95, right? So look at this table. So we are looking at the probability 0.95. So 0.95 will be some around here, 0.94095 and 0.9505. So let's pick this one. So it has the value 1.65, right? So this quantity, or this argument, in order to, so this probability is 0.95. In order to have this probability that 0.95, this has to be, that is c minus 200 divided by 20 would be equal to 1.65, and from here we can find the value of c, right? So that will be, so this will be 16 दूना 32 और एक this will be 33 plus 200. So overall the maximum capacity that is allowable in the container with the probability that it exceeds with 0.05 is 233. Alright, now let's look at one more problem. Okay, now let's look at this problem number 3. A container has a fixed capacity of 210 kg. Each package to be loaded into the container has random weight modeled as an independent exponential random variable with parameter half. Let n denotes the number of packages loaded. The logistic company wants to ensure that the probability of exceeding the container's capacity does not exceed 5%. What is the largest number of package, that is n, can be loaded? In this problem, we are given the capacity of our container. We want to have the small probability of exceeding that capacity. How many packages should you try to load? Right? So we have given that the probability that the overall weight of the packages exceeds the actual capacity of container, and this probability we have given as 0.05. How we can proceed? So in this, now we have given this and this, we are trying to find this, how many such packages or how many number of packages that we need to have in order to have this relation. Again, we are going to first of all make the standardized version of this random variable. So in order to do that, we are going to subtract the mean, and mean will be n times, because n is unknown, n times 2, right? Because 2 is the expectation of one single exponential random variable, and we have such n random variables, so the overall expectation of the sum would be 2 times n divided by the standard deviation of this. So the standard deviation would be root over 2n, right? So we have, I think you would be able to find that what will be the standard deviation of this random variable Sn, right? And we have already done for last 2 problem, and this we will be doing on the both side. So subtract 2n and divide by 2 root over n, and that should be equal to 0.05, right? And once we have make the standardization as per the limit theorem, we can consider this as a standard normal random variable. So let me rewrite this again. So let's consider this as Zn greater than 210 minus 2n divided by 2 root 2 divided by is equals to 0.05. Now you can consider this as per the central limit theorem as a standard normal random variable. The same probability can be written as 1 minus p z less than 210 minus 2n 2 root over n. That is equal to 0.05, right? And why we have done like this? Because the table that we have given is of the normal table. So this table is for the probability z less than is equal to z. So now we can make use of the table, right? And so let me first of all separate this probability that this zn less than equals to 210 minus 2n divided by 2 root n, that is equal to 0.95, right? So for what, so this probability calculated to 0.95. so what argument that we need to have such that this calculation have the probability that is 0.95. so, and this is, we can treat as the standard normal random variable, right? So we can write this as in terms of the CDF, that calculated at this, and this is equal to 0.95. so for what argument we have this 0.95, we can look at the table. So 0.95, the probability is 0.95, so it will be somewhere around here for the value that is 1.65, right? So that means this should be equal to divided by root 2, and that is equal to 1.645, right? And from here you can calculate the value of n, and it will be not a integer value, but the number of packages should be integer, so it will come around 89 or 90. So you can choose either 89 if you are conservative, then you will try to put a less number of packages, rather than putting 90 packages you will put 89 package, so that we do not exceed this probability. So if you are conservative, otherwise you will be putting 90 packet. So doesn't matter, the answer is correct for 89 or 19, whatever you will write. In the exam there will be no such kind of confusion, it will be absolute answer, right? You will not have such kind of confusion that it will be 89 or 90, right? So n is equals to 89, right? So from here you will have to use the calculator, because from here you will get the quadratic equation, and using solving that quadratic equation you will get around 89 or 90. All right,